Hello and welcome to ResearchPod. Thank you for listening and joining us today. In this episode, we'll delve into the research of Dr. Jun Young Cheong, Reader in Materials for Green Energy Technologies at the University of Glasgow. In his most recent research works, Jun demonstrates that gum waste from a tropical tree can be used to fabricate a crucial component in rechargeable batteries. This finding could have significant benefits for the environment and contribute towards the low carbon footprint as well as net zero carbon neutrality, since the water-soluble option of plant gum could replace the unsustainable materials currently used in this element of battery manufacture. Since entering consumer markets in 1991, lithium-ion batteries have undergone continued advancements. Due to their exceptional electrochemical properties, they are now used in portable electronics and electric vehicles. All batteries, with lithium-ion being no exception, feature a component called the anode. This element plays a crucial role in the charging process as it enables the current to enter the device. Previous research has established that natural graphite can serve as an anode material, providing the additional benefits of reduced CO2 emissions and better stability compared to artificially manufactured alternatives. Within the anode of the battery are polymer binders. These binders facilitate the cycle of repeated discharge and recharge of the battery. In natural graphite anodes, the binder is most commonly composed of polyvinylidene fluoride. This material can only produce anodes with a lower capacity of electrical charge, limiting its usage to smaller electronics. Polyvinylidene fluoride may also have harmful effects on marine life when the material enters and degrades in aquatic environments. A more worrisome issue is that polyvinylidene fluoride is dissolved in the NMP or N-methylpyrrolidone, which can potentially be carcinogenic. Finding a natural binder that can handle higher charges whilst avoiding environmental pitfalls is therefore an exciting prospect for the lithium-ion industry. Water-soluble binders have emerged as a greener alternative to polyvinylidene fluoride. These binders offer the advantage of natural availability as well as being easy and safe to disperse in water. Water-soluble binders are also known for their cross-linked structures. These structures enhance the chemical bonding that occurs within electrodes, offering the potential for handling a greater electrical charge. In the research carried out under his group, Dr. Jun Young Cheong uses the gum of a tropical tree to create a water-soluble binder for natural graphite anodes. This form of biowaste from the Coclospermum gossypium tree would offer both cost benefits and an abundance of supply, as well as being more friendly to the environment. However, tree gum is a novel choice for battery anodes. Previous research has focused on other applications for this form of biowaste. Therefore, Dr. Cheong worked alongside colleagues to compare the performance of this water-soluble binder with the conventional material. This would test whether the biowaste binder would be suitable for use within the anodes of lithium-ion batteries. Researchers began by extracting the target molecules from the tree gum. The natural graphite anode powder was then mixed with either the water-soluble or conventional binder. The resulting blends were contained in copper foil and combined with lithium metal and an electrolyte, forming two half-coin cells. This form of cell would allow for researchers to focus their investigation on the performance of the anode. Various analyses were then conducted to evaluate the anode's structural, chemical, and mechanical properties. Researchers measured the current traveling through the cells using a procedure called electrochemical impedance spectroscopy. This confirmed that the anode with water-soluble binders exhibited lower resistance than the conventional form, allowing a greater flow of electrical charge. Furthermore, researchers checked for cracks or superficial damage to the anodes using an electron microscope. This demonstrated superior structural integrity in the anode built from water-soluble binders, suggesting that using the biowaste binder could help improve the reliability of lithium-ion batteries. Researchers moved on to conduct a cyclic voltammetry analysis. This test compares the rates of electron transfer between the binders and their respective anodes. Such a test would provide a more detailed picture of electrochemical activity compared to the previous spectroscopy method. This is because cyclic voltammetry focuses on the oxidation and reduction reactions that drive battery operations, with oxidation bonding substances with oxygen and reduction removing this element. By measuring these redox reactions, the researchers established that the two anode builds provided similar electrochemical performance, with some improvements found in the use of water-soluble binders. This means that the biowaste anode was slightly more efficient in producing the chemical reaction that powers a battery, giving a further indication of the superiority of this binder form. Researchers finally tested the stability of each anode build. After 200 cycles of discharge and recharge, the traditional anode experienced capacity degradation. This means the unit could not store or produce the same amount of electrical energy as it could previously manage. Meanwhile, the water-soluble based anode maintained a higher capacity for up to 360 cycles. While researchers increased the amount of charge per second flowing into the anode, these changes became less pronounced and the two binders produced similar results. Nevertheless, biowaste build generally exhibited superior stability and performance compared to the conventional product, making it a promising choice for biochemical applications. Overall, the study highlights the potential of using water-soluble binders derived from plant biowaste as an eco-friendly alternative to conventional binders in lithium-ion batteries. The unique properties of the plant gum contribute to slightly improved mechanical strength, electrode integrity, and electrochemical performance, making it a promising candidate for the next generation of energy storage. As previously explained, binders form part of the anode of a battery. The broader anode housing may be manufactured using natural or optimized graphite. The natural graphite anode has generally shown somewhat poorer performance compared to those made from synthesized graphite. However, the study shows that binders from plant gum can help reduce the performance gap between anode variants, offering the potential for an entirely greener lithium-ion battery that maintains similar overall quality and reliability to the traditional builds. The lithium-ion industry will also find cost and abundance benefits in greener materials, suggesting that battery production may undergo a general shift towards these alternatives, which are friendlier to the environment. However, Dr. Cheong and colleagues stress the need for future research to optimize the performance of biowaste materials. This could enhance the electrochemical performance of greener battery builds and bring them closer to conventional products. Furthermore, since plant biowaste is a natural substance, it will undergo changes throughout the seasons that may alter some of its properties. Therefore, it is important to either intervene to control these variables or adapt to such changes so as to produce a binder product that remains consistent for commercial use. The study, therefore, demonstrates the potential of using water-soluble binders from plant gum in future anodes within lithium-ion batteries. Indeed, the same material may prove successful in the cathode component, which handles the flow of charge out of the battery. As such, the work by Dr. Cheong and colleagues provides valuable insights that could make the manufacture of energy storage systems greener, cheaper, and more sustainable than current methods. Already, Dr. Cheong and his collaborators are teaming up together with Harmony Remedies, one of the leading companies in India on using gum materials for various applications, including drugs and oncology. And they have already initiated discussions on potential product development through further investigation. This is a great example of how the research carried out in the laboratory can be translated into the industry circle, which brings a significant impact not only in academia, but also in society as a whole. That's all for this episode. Thanks for listening. Be sure to view Dr. Jun Young Cheong's original article in the show notes for more of the details from this study. And don't forget to stay subscribed to ResearchPod for more of the latest science. See you again soon.